Okay, I'm going to show you this video here. I'm going to show you how to analyze it. I'm going to analyze this video. I don't know about you, but I like to carry my phone with me, and when I see something really cool, I record it. And so in this case, let me show you this video. It's a minute long. I'm just going to scroll through it. I was at a soccer game, and the sun was setting, and you could see it. There, it's going down below that building right there. You see that sun? Nice. Okay, so what I want to do is to use this video to measure the rotation of the Earth, the rotational speed of the Earth. And I don't know if it's going to work. I haven't done it yet. I did do part of it, okay, but I haven't done it. So what we're going to do is to use tracker video analysis. So let me pull that up right here. So here's tracker video analysis. So I have the video already loaded in there because sometimes it can take a while. And so this is a free video analysis program. It has a lot of features, really nice, I think very useful to me. So what we can do is mark the location of an object in here, and it will give us essentially the pixel location as a function of time. Now, if I want to convert pixels to something else, in this case I want to convert it to angular size or angular position, then I need to scale the whole thing. So I need to know the angular field of view for this. And this is the iPhone 13. I think it's the 13 Pro. Is that right? 13 Pro. It's got the 3x zoom video camera, and that's what I used here because the sun's really small. So what I need to know is I can set the scale here, and let me go ahead and set that up. So I go to here, new calibration stick, and this will allow me to say what's the pixel to angular size correlation. And so we use this for distance too, but I'm not going to use it for distance. I'm using it for angular distance. So I can go up here, and I can put one end on one side of the video, and the other end on the other side of the video. I'm not doing a great job because I actually already did this. And then I can change this value to whatever I want. So what is the angular field of view for the iPhone 13 Pro video camera? Now, you could possibly look this up. I had trouble looking this up before, so I did it. I did an experiment. So here is, where am I? Is this it? Yeah. So this is a blog post I did on Medium, the angular field of view for the iPhone 13, blah, 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 blah. There's an example. And what I did is actually move different distances away and find the angular size as a function of distance to get a linear plot, and that really works best. You can also, one of the great things if you want to look at the angular field of view of a camera, especially one that can take pictures of stars, is to use stars. Because here you can see right here, this is Orion. And especially if you use diagonal elements, it doesn't matter where you are, the angular field, the angular size of this is the same, right? So you don't have to worry about how far you are from if you look at, let's say, a house, you said, I'm 10 meters from the house and the house is this size. Well, if you get that size wrong, then you're wrong. But here you don't have to worry about the size because we're all the same distance from the constellation. So it's a great way to scale your camera. And then what I did is to use that image, and once I know the angular field of view of one size photo, and I think that was a 3x zoom photo. I'm not sure. No, it wasn't, because you can only do that for this 1x zoom. Then I can just kind of take a picture of my backyard with with the wide angle, the normal, and the 3x zoom, and line them all up, and then I can use video analysis again to kind of get the ratios. And then did the same thing for the video, and here's the answer that you've been waiting for. How wide is the 3x zoom video? It has an angular field of view of 0.329 radians, and that could be a little bit wrong, but I'm pretty happy with this. Oh, it's 13 Pro Max. That's what I have. That's what I have right there. Okay, so over here I can just do this. 0.329. So now I know when I measure things on here, it will measure it out of that maximum angular displacement. Now, there's a couple other things I need to do. The first is, this is a 1 minute long video at 30 frames per second, and I don't want to mark the location of the sun every frame. That's a lot. So instead, I want to do it once a minute. Wait. Yeah, once a minute. So if I go up here to this button, this will give me my video properties. So it starts at frame 0 and it has a step size of 1. I can change it to 30. So if I do that, I'm just going to get I'm going to skip 30 frames every time I click. And that will make it a little bit easier for me, less clicking. Okay, now there's one other thing I need to do. I can put my origin, here's my origin, and I'm going to put it right over here to mark it with something that I can see. And we can zoom in on this just a second. But I record this just on a whim, so I didn't have a tripod. So I try to keep it as steady as possible. I propped it up against something, but it still moves. So what I want to do is go up here to coordinate system and fixed origin, turn that off, fixed angle, turn that off. Now when I skip through, I can move this origin around and make sure it's in the same spot each time. So let's zoom in. Oh, I want to do another thing. I want to measure the angular size of the sun as seen right here, just to get, I know it should be around half a degree. I want to see if I'm way off base, just as a, so I'm going to do a tape measure here, so then I have that. I'm going to pull it up here. Now let's zoom in on the whole thing. Let's go to 200%. And I think I need to go up. And then over here, there we are. Okay, so there's my sun. Now I can, this is just like the other tool. I can put one on each side. I'm kind of guessing on the other side of this because I don't really have the full sun. So that's 7.68. So let's convert that to degrees. Oh, it does it. No, it doesn't. I think it does it in degrees. Well, that's fine. Let's just do it manually. So I'm going to use my little calculator here. So 0.00768, sorry for leaning in, I just can't see, times 180 divided by pi. I get 0.44 degrees. So that's pretty close to half. So it might not be perfect, but we're in the right ballpark, so that makes me a lot happier. So what I want to do is let's put this right there at the corner of that house and line this up with that roof like that. So every frame I want that to be true. So now I can just skip to the next frame, and then I need to go through all the frames, not worry about the sun. I just need to go through each frame and move this so that it's back in the exact same spot, and then just keep doing that. Okay, and that's 60 frames, and it's kind of slow because it's a big video, and I don't want to do that. So if you've ever seen these like baking shows where like they say, okay, now you need to make it cook for 30 minutes. We're not going to wait for 30 minutes because I already got one done. I already got it done. Okay, so I went through and moved the frame in each, the origin in each frame, and there I have it right there. So now let's jump back in time all the way to the beginning. Okay, and what I want to do is to mark a location on the sun. And what I want to, I don't have the center. And I could, and this would be fun actually, to mark multiple locations and use those multiple locations in each frame to kind of find the center of the sun. That would actually be a really good idea. But I'm not going to do that. I'm just going to kind of guess, right? I'm going to guess at the point. Let me skip here to the video. And you see there, if I look at like a point right up there, which way is it going? So I think I'm just going to pick a point like right around there. Let's try that. So now what we do is go to Track, New, Point Mass, and I'm just going to try to eyeball it. So I'm going to hold down the Shift key, and it turns into that little marker thing. I'm going to put it right there. I'm going to click it. And it moved to the next frame. And it should move again. It's not gonna be perfect, and it's okay that the frame moves around because I'm adjusting for that in the with that origin right there. So I just need to click this. It shouldn't take too long. 60 clicks, right? I'm trying to be in the same part of the sun, even though I'm sure I'm not exactly. But I think it will all wash out in the end. Keep clicking. And remember, we're in angular position as a function of time. And you know, you can do this. Don't look at the sun. You should know that, right? But the camera is fine to look at the sun, especially when it's low on the horizon. Now, Also, there should be some atmospheric distortion in this case because you're looking through a lot of the sun and a lot of the atmosphere. But again, this is not perfect. What you could do if you want to do a better job is to look at the moon over doing the same thing, because the moon's about the same size. It's a lot less. You can look at it when it's high in the air. I would try to get a reference object in the same frame, like a tree or something like that, so that you can see how the camera moves, or use a tripod. But then I wonder if you could even measure the motion of the moon with respect to the background stars. Oh, that'd be cool. So you could actually, I wonder if you probably couldn't see the background stars with the video camera, but you could take a picture every minute and do the same idea, then put it all together. Okay, so now we're gonna have a problem because this is not moving in the X or the Y direction. Okay, you'll notice. So, but that's fine. So right here, we can do this a couple ways. So right here, I have my X position in angle in radians per second, radians versus, and my Y position. So it looks fairly constant both directions. One thing I could do is to find the X angular velocity and the Y angular velocity, and then the total angular velocity is going to be the square root of the omega X squared plus omega Y squared. I think I can do this. R position magnitude. No, that's R. I could do Vx, V velocity magnitude. Let's just do what we had. Okay, so I had that at X. Okay, so let's do this. I'm going to analyze this. I'm going to click Analyze. And it's going to bring up a graph. And that's pretty nice, right? There's some fluctuations in both where I mark the sun and in the motion of the background where I put the origin. So, but overall, over 60 frames, it looks pretty good. So I'm going to go up here to Analyze, Curve Fit Line, and then it fit a best fit line. It gives me X equals A, T plus B, and A is 3.07 plus or minus 0.8. So let's write that down. I'm going to put omega X, I'm going to show you this in a second, is 3.07 radians per second. And I think that sometimes they put like the scientific notation over here on the side. E to the negative 5. See? So it is times 10 to the negative 5th. Okay, so now let's do the same thing for Y. So I'm just going to close this. I'm going to go over here, right click, and go to Analyze. Okay, so it's showing both X and Y. I can just turn off. I think I can just analyze. If I just click Analyze, Curve Fit Line, I think I'm on the Y value. No, it didn't. Okay, so let's just go over here. I gotta see this. Let's turn off the X. So there's my X values. I'm going to turn those off. No. That must be Y. Turn this one off. Turn off. I didn't want to turn that off. Okay. So, let's see. Why isn't that doing that? Oh, no, it is. It did it. It fit it. That's a different fit. Yeah, because that one's negative. I wasn't paying attention. Okay, so I have negative 4.36, so omega Y, 4 point, I don't care about the negative sign. And then what does this say? It's just kind of slow right now. Okay, 4.36 times 10 to the negative 5th. Okay, that's negative. Okay, so I think let's just jump over here to the paper and just do a little bit of calculation here. Paper view. Okay, so there's my omega X, there's my omega Y. So omega is going to be the square root of omega X squared plus omega Y squared. So let's, equals. So let's do that in the calculator. I'm just going to do it manually. So I have, I don't need to worry about the 10 to the negative 5th. That's just going to factor out. So I can say 3.07 squared, clear, square root square root 3.07 squared plus 4.36 squared, close parentheses, equals. So I get omega equals 5.33 times 10 to the negative fifth radians per second. So based on that, how long would it take the Earth to rotate? So let's say omega is delta theta over delta t. So let's say delta theta is 2 pi, that's one rotation, over delta t. So delta t would be 2 pi over omega. So let's do that. So I'm going to do, can I do this 1 over here? Let's do, this is clear. Okay, so 2 times pi divided by delta t, which is 5.33 times 10 to the negative 5. And I get delta t is 1.179 times 10 to the fifth seconds. So how many hours is that? So say delta t is 1.179 times 10 to the fifth seconds. And I can multiply that by, I know that in 1 minute there's 60 seconds, and in 1 hour there's 60 minutes. So I can say 1 hour over 3,600 seconds. So if I divide that by 3,600, I get 32. I get 32 hours, 32.7 hours. Okay, so it didn't quite work, and I'm okay with that. But I think I could do a better job, and that could be just optical distortion. I'm not really sure why. I still had fun, so there's that. Okay, so tracker video, I'll link to the Medium post down below. I had fun doing that. Hope you had fun too, and I will talk to you later.